Okay. You guys see my share screen?
Yeah.
Okay. So yeah, today I will run over the ADS EM simulation tutorial. So in millimeter wave design, you have to run EM simulation because like at very high frequency, even very small piece of conductor gonna have a lot of inductance, and you have to capture the effect of that inductance in your layout, because like that can be like an important contribution to your matching network, for example. So this one is a layout. Before we need to start ADS in Linux. So you can go to command Windows and you type ADS. Okay. And so you need to open the workspace or the library. You put the design in. So in here, let's see. So you go to File and you go to Open Workspace. And in here, I have a folder called ELEN6320 underscore work. So this folder, when you download the file I attach in the announcement on coursework, when you download that file and then you extract it, it contains that folder. So you can use that folder as your workspace. And so you click in here and click choose. Yeah. So this one has like a list of layout and a stack up of your technology. So in here, I already have one layout, but I'm gonna create a new one for this tutorial. And you can also see there's a substrate definitions. And so when you double click on this one, you can see like the layers we can use for layout. And these are like substrate, and these are M1 to M6 metals we use to for layout. And so normally when you receive like a PDK from the foundry, they also give you this substrate definitions. But in here for this course, we sort of create a custom substrate, and we use that for layout. Let's see. If you guys see anything you want to ask more, let me know. So we're gonna close this. Okay, so we're gonna start the layout. So you can go to File, New, and Layout. So so for naming, in general, it is better if you give like very like a sort of descriptive name for the layout. So you sort of like in the future you can have like a bunch of layouts and you can see the name and you can know which one you should look for. So in here I gonna in this tutorial I'm gonna create a coplanar waveguide, and so I'm gonna type like CPW for coplanar waveguide, and the width is 10 micron and the spacing is 10 micron. And let's say the length is 200 micron. So that is how I normally name it. And I simulate it for 60 gigahertz. So I type 60G and create layout. So let's see. So you can check. You can go to option and go to preference to check the unit of the layout. I think you can either choose the unit in meters or in mil. But in here, the default is in meters. So as you can see, like the unit here is in the micrometer. And then okay, draw top arrow. What is substrate? Let's see. Okay, so we have the layer sub windows here that show you all the metal layers you can use. They also provide the via as well. So like PC M2, M3 is the via you use for between M2 and M3 layer, and so on. Okay, so we're gonna draw the top metal on M6 first. So let's see. So we click on M6 and we can select like insert rectangle, or we can press R on the keyboard. So when we press it, you can draw the rectangle. So and then we can put in the dimension here. So we want the width to be what is it, like 10 microns, and the height is 200.
Hey Fong, I have a question.
Mhm.
So we design our schematics in Spectre and then do our layouts here because we need to model all the connects and inductances, right? Is that the only reason? Or
Yeah, so are you talking about the project or the design in general?
in general, in general.
Yeah, so in general, you are true. So you are gonna go to Cadence and you draw the layout in Cadence. But like Cadence also have like a simulation tool where you can simulate the inductance, but that tool is not very accurate. So people prefer to use some ADS, or they use FFS or EMX. So in here, I show you how to do ADS. So normally, in general, when you have a layout in Cadence, you're gonna export the layout in GDS file, and then you import that file into Keysight ADS, and then you have the exact copy of what you have in Cadence in ADS, and then you can run EM simulation in ADS.
So ADS is more accurate in terms of EM simulation than Cadence is what you're saying, right? For
yeah,
layout. Okay, got it.
Let's see. So I think people also do inductance simulation in Cadence, but probably for lower frequencies. But I don't work at that frequency, so I'm not like very knowledgeable about that process. Okay, so we can go to draw M6 here.
We can't do schematics in ADS, right? It doesn't allow that, right?
So yeah, you can do schematic in ADS, but like ADS is not very how would I say, it doesn't provide like as many tools in compared to Cadence in terms of schematic design. So yeah, people like normally they design in Cadence as well. If we have time, I can show you how we do like ADS simulations.
Okay, thank you.
So it's a rectangle with M6 here. I think we can check the dimension as well. So you can go to insert and ruler. So you can select here, and then you can select here for the dimensions. So yeah, so we have the dimension here, but normally we can just use the units, the numbers in the bottom right corner. Let's see. So okay, we set the rectangle coordinates and dimensions. So let's see. So why the width is 5? Okay, so I might do different than the tutorial, but you got the idea. Okay, so, and then we're gonna draw the ground. So this one is M6 is like the where the signal gonna travel. We also need to draw the ground for the signal path as well. So the ground constructed on M2, M3, and M4. Okay, so we're gonna draw a rectangle on M2 and 3 and M4. So M2, put it like this. So in here I design like it's called like 10-10-10 complainer waveguide. It means that the width of the signal path gonna be 10 micrometer, and the spacing between the horizontal spacing between the conduction. Let me draw it. So we're gonna draw something like this. This one is like top view. So and then we also have this one is signal, and we also have ground shield as well. So this one is ground, and this one is also ground. And this one is on M6, M6, and M6. And when I say 10-10-10 transmission line, it means the width of the signal path is 10 micron, and the spacing is 10 micron. Okay. So, let's see. So in general, we want the width of the ground gonna be around like 20 micron. So the width of the ground, let's see, it's gonna be 70. Width 70.
Sorry, we're on M2.
Yeah, we are on M2. So
are you saying like the M2 is at the ground?
yeah, M2, M3, M4 are ground.
Oh, M6 is the signal, and M2, M3, and M4 are ground.
Yeah. So
okay.
Okay, so let me do it again. So you have signal. You just close. Okay, so you have this one, the top view. So you have signal here, and you have ground, and you have M6 here, you have M6 here, and you have M6 here. And so like in horizontal view, you're gonna see something like this. So this one is signal, this one is ground shield, this one is also ground shield, and this one is M6, M4. I think this technology doesn't have M5, so this goes straight from M6 to M4. And let's see, you have M2 to M4 here. Let's see, so yeah, we're gonna have something like this.
I see. So you're stacking the M6 on top of directly contact with M4.
Yeah, so in let's say, so yeah, so we have not directly, but we have to connect them with the via.
Okay.
Yeah.
Sure. And then you're saying like the M6 are all 10, but your screenshot in this size for the M6 metal is 5.
Yeah. So so in here I draw different dimensions, but in the tutorial file I draw different dimensions, but like the size of the coplanar waveguide gonna let's say the characteristic of the coplanar waveguide gonna depends on the dimensions of the width and the spacings. And then we have to choose which width and which spacing is correct in order to provide a 50 ohm impedance.
I see.
So yeah.
Is it like linear? So for example, we do 10 in width instead of 5, and then the spacing is going to be double, which is 10, like 10 width and 10 spacing. But if you do 5 width, then you will do 5 spacing.
Yeah. So
okay.
In general, true, but you can also play around with the spacings as well, because like like the characteristic impedance of the transmission line is like square root of L over C, right? So this C is gonna depends on the spacings. So if you like reduce or increase the spacing, this C gonna be different, and you can use the spacing as a way to tune the Z naught until it gets to 50 ohm.
Sure.
But like as other rule of thumb, well, we normally use 10 for width and 10 for spacings.
Sure.
So I set it to 200. Okay. And this is now I set lower X to 0. Okay, so we have M6, M2, and we do the same for M3 and 4. So I just make a copy. So you can do copy M2 by clicking on M2, and you press Ctrl C and Ctrl V to copy it. And copy again, and then you name this layer M3 and this layer M4. Okay. And and then we can select these two metal layers, and then we type the coordinate of these two metal layers, 0 for X and 0 for Y, so that they overlap each other. Okay. Okay, so we have M2, M3, M4 on top of each other, but we also need to connect them because like in between them there's substrate. So we're gonna use via to connect them. So there's a layer called PCM2, M3 and PCM3, M4. So we're gonna use two layers to connect M2 to M4. Let's see. So make sure the width, the dx is 20 and dy is 200. Okay. So that is M2, M3. And we copy that and name it M3, M4. Set the coordinate to 0 and 0. Okay. And then we copy these two vias and put it here. Okay. Let's see. Oh, actually, yeah, actually for the vias on from M2 to M4, we want to like fill it on all area of M2. So we don't do it this way. So we're gonna actually fill it all the way. Set it to yeah. Okay. Yeah, because we are drawing the ground underneath the signal, so we need to fill it all the way. So now we got to the step where we're gonna draw the side shield or the ground shield on the two sides of the signal. So if you remember the pictures I draw earlier, you're gonna draw the side shield on M6. So you press in the layers sub window, you choose M6 and you draw a rectangle. Okay. And you select the width to be 20, the height to be 200, and the coordinate to be 0 and 0. And then you so you have M6 here, and then you have to draw the via to connect M6 to M4. So you use PC M4 M6 here to draw again. But again, I'm gonna copy M6 and then I choose the layer to PC M4 M6. 0, 0. Okay, and then we copy the side shield from the left and we paste it to the right. So this one will be 60, 0. Okay, I think we have the coplanar waveguide layout. Now we need to find a way to like EM simulate this structure. And so the way we do it is we have to create pins. So pin is a way to excite the signal into the structure. So if we put let's see, M1 here, let's see, and then again, you can do the same thing for M for P2. So we have to define which layer this pin attached to. So for let's see, for P1, we want it to be attached to our M6. So we click on the pin, and then we select M6 for layers. And then we do the same thing for P2. We want to select M4. Okay. And then I select these two pins and I copy, Ctrl+C, Ctrl+V. And so I while selecting it, I can rotate it by select Ctrl and R. So that allows me to rotate the arrow. And so we'll put it here. Okay. Let's see. Yeah, so this explains what the step I did before. I set P1 to M6 and P2 to M4. Okay, so now we can check if our layout is correct by using the 3-dimension view. So you go to View and you select 3D view. Okay, so let's see. Yeah, so in here you sort of see what we want to draw, right? So we have a ground plane on M2 and M4, and they are all connected to each other with vias. And then we have two ground shield on M6, and then we have the signal path on M6. Okay. So I'm gonna go back to 2D view. So check one more thing. Okay, so we have 4 pins here, but we need to create 2-port simulations. It means like one pin gonna be positive. terminal, and one pin going to be negative terminal. So in order to do that, we go to this symbol. And then for P2, you're going to drag it to the negative symbol of the terminal 1. And P4 go to negative of terminal 2. Okay. And then you go to EM and create EM setup view. Press OK. Okay, so again, I think I went ahead in the tutorial, but in this slide it shows you how to set up the port in positive and the negative terminal. So this one I already did, but again, you can go to a port in here, and then you can define the positive and negative pins.
Can we see that in the 3D view you just showed? The positive and negative.
Let's see. So yeah, in here you can also see a 3D view by selecting the rectangle. Save. You want to see something like this, right?
Yeah, the ports are not assigned in the 3D view, right? So they're not able to see that.
Let me see. Yeah, so let me see how we can see the port visible in the 3D view. Maybe select this. I'm just checking if the pin like physically connect to the metals, but it seems like they are connected. Oh, okay. So yeah, with this view you can see the terminal. So you see port 1 here, and you see port 2 here.
Okay, thank you.
Yeah. So essentially, what is happening here? What happening here is that we, like, you can imagine, like, physically we attach a signal into like the M6 and M2, and then we excite some VS here, and we measure IS, and then so from that we can capture the S parameters behavior of this structure. And then the same thing on the port 2, we also have like positive and negative terminal attached to M6 and M2. So, okay, so again, go back to EM view. So we set up the port, and now we need to set up the frequency plan. So that allows you to select which frequency you're going to run the simulation on. So you go to a frequency band tab, and in type you select linear, and then you for f-start you select 2.5 gigahertz. Let's see, let's say tutorial. Okay, and f-stop is 60, and the number of point is 24. These things are not too important, but let me see. So for mesh, you normally want to higher mesh as possible, but like again, like when you select higher mesh density, it's gonna take more time for the simulation to run, because you need to it's gonna divide your structure into like different polygon, and so like the smaller polygon, the layout need to the ADS need to EM simulate, the more time it's gonna have to run on simulations. So normally I just like for moderate accuracy, I just select 20, but you can select 40 for more accuracy. And let's see. So these all fine, resources fine. Okay, and then you can select simulate. And so if you look at the message, you can see like the matrix size is 484, which is reduced to 345. So if we in the options and in the mesh density, we increase this one to, let's say, 60. This number going to be increased to like higher number. So we maybe have to wait a bit until it runs to 60 gigahertz. Let's see what is left. Is it clear so far for everyone?
Yes.
Okay. Yeah, maybe for 5 more minutes, and the simulation gonna be done.
But why does it take so long for the simulation? Is it because of the mesh size being 20 or any other parameter?
So I would say this is considered short, because like when long, I would say like 1 hour for one frequency point. I think this one is like relatively fast. So for example, in my circuit I'm working on, like yeah, one I need to simulate like a matching network structure, and yeah, one frequency is gonna take like 50 minutes or something, and so I have to simulate from DC to 500 gigahertz, And so I normally have to like start the simulations and wait for like 1 day and then come back to see the simulation results. So this one is fast.
Okay, yeah.
But yeah, again, so if you want to reduce the simulation time, you can either select like less number of points you want to simulate, or you can reduce the mesh density. But if you have too low mesh density, then your simulation is not going to be accurate. So I think you can sort of see the mesh density here. So each, like you can see sort of like a boundary, and so the ADS gonna treat each boundary as one piece, and then it divided the structure into different pieces. So if you select like 40 for mesh density, you're gonna see more boundary, and the structure gonna be more accurate. I don't think like 20 is accurate enough, but for tutorial, we just need 20. Okay. So the simulation is done, and then this result window gonna show up, and so we want to first of all we want to save, and then we want to save this result into an SP file, and then SP file is like a file that allows you to run simulation on Cadence. Oh yeah, Cadence. Okay, so you go to tools, and you select data file tool. And then you select write data file from dataset, and you select the dataset we just simulate. And then what you need to do is copy the file to the output file name, and select write to file. So you can also click on browse to see where that file is gonna be saved to. So it's gonna be saved in the data folder in the library we just created. Okay, so we just have a file, and then so this is like done the tutorial, but I'm gonna give you one extra step, which is how we're gonna see that result in schematic level. So we close this, and then we close this one. So we close. Okay, so in here you can create a new file, and then you can go to schematic, and then type CBW width 10 micron, spacing 10 micron, length 200 micron, 60 gigs, and test bench. Yeah, so I think some of you have a questions about if ADS has a schematic simulations, and this view is a schematic view. So in here you can type term for port simulations. So you insert port 1 and port 2, and then you can search for S2P for an SP module. Around the connections. And so you double click on the symbol and select the SP file you just simulate. So this one is a file we just saved. So press OK. And then You can search for s_param for SP simulation. Yeah, so start is from 2.5 gigahertz and stop at 60. Step is 1 gigahertz is fine. And then you click on this gear, and that's gonna run the simulation for you. So you can click on this square for select which kind of result you want to plot. So in here, I'm just plotting, let's say S11, and you double click on S11, and then you select you can either select the unit in dB, or you can plot the real and the imaginary part. So we select S11, and we do the same thing. We can plot for S21. Yeah. So also you can so this one is S parameter simulations. You can go back to your schematic and select on this SP simulations, and in parameters you can click on Y parameters as well. Normally I use Y parameters because it's easier for me to do calculations. So you can select Y parameters and you save, and then run the simulation again. Let's go this. Yeah, and so you select the box again, and in here you can see, like, you can plot on y21, y11, y12, y2. Yeah, again this time let's plot the real part and the imaginary part, and this is what you see. So in ADS you can also select equations, and then you can type like from here you can sort of like you can do like extraction of this model. So in for example, in the transmission line, we can model the transmission line in terms of RLCG model, if you guys heard of it. But again, we can do the calculation, we can do the math to find the RLCG values in terms of Y parameters, and then you can import that equation in here. And from that, you can plot RLCG values in ADS as well. Yeah. So I think that is done of my tutorial. If you guys have questions, please feel free to let me know. Or otherwise, I'm gonna stop the recording.
Can you also briefly show like how to do for an inductor or something? Just
For inductor?
Yeah.
So you mean like for layout?
Yeah, for the layout.
Yeah, so for the layout, let's see. Maybe I can quickly show how to do it. Let's see, file new. The thing is, like, most of the layout shape gonna be defined in the PDK. So in Cadence, you can have like an option of which inductors you want to use and the dimension of the inductor as well. But in this course PDKs, we don't have that luxury. So we have, if you want to have your inductor in your schematic, then you have to draw your own inductor. But in here, I'm gonna maybe just quickly show how I would draw an inductor. Okay, so you can select insert and select path and select the width. Maybe set the width to 10 micron and style. Not sure, maybe square. Let's see what it does. So you can draw an inductors. Maybe something like this. You can select M6. So you can you can do more careful layout to make the shape more symmetric. And then so you have M6 for inductors, but you also need like a ground to define the negative part, negative pin. So you select M2 and press R and draw a rectangle. Let's see, maybe we'll stop here. Yeah, and then you can define the part. Sorry, the pin for P1 and P2 and P3 and P4. Let's make sure P1 is on M6. Okay. Then P3 and M6. And in part editor, you drag P2 to negative and P4 to negative. Yeah, so that is normally how I would draw the inductors and simulate it. So if let's say like you want to have like 60 picohenry and you draw this layout and you realize the inductor you have is only let's say 50 picohenry, and so what you have to do is you have to manually increase the dimension of the inductors so that your inductance go to 60 picohenry.
Okay, thank you.
Yeah. That's a different trick. So you know, like because we have a ground plane underneath the inductors. So in the class, the professor draw sort of like a parasitic model of the inductors that has inductors, some resistor, and some capacitor, some resistor. This model, right? So this capacitor, C shunt, that come from the metal M6 to M2. So if like this capacitance can like affect your performance, especially at high frequencies, what you want to do is to reduce this capacitance, and the way you want to reduce it is to sort of like draw. You want to remove the ground plane underneath the inductors, but again, you still need some sort of like ground, so that you can put a negative pin on it. And so what you need to do is to So you can press Shift C, and then you sort of like chop the. I'm sort of like doing it in a incorrect way, but I just can sort of like make a hole underneath the inductor only, so that shunt capacitance can be reduced. Yeah. Okay. And any more questions? Maybe I can stop and share screen.